Okay, let's get started. Oh, what is this? Oh, okay, let's get started. Good afternoon, everyone. So we finished the network layer, and we finished talking about routing, correct? So there were a couple of issues that came up when we talked about routing, specifically two issues. So remember, the two routing algorithms we discussed were the link state, which is Dijkstra's algorithm, and distance vector, right? And for each of those, for link state and for distance vector, there were a few, if you will, subtle issues. Okay, so I want to just talk about a couple of subtle issues for each of the two algorithms. All right, we briefly discussed it when we talked about the two algorithms, but I want to maybe elaborate on those because they can be a little bit tricky. All right, so before I continue, can I just check, are there any questions on what we've done so far? Okay, so routing, I hope, is fairly clear. Okay, so remember, the two algorithms were distance vector and link state or Dijkstra. For distance vector, we saw that we also use this as a little bit of review. Okay, so distance vector is a decentralized algorithm, okay, where nodes have local knowledge. They have knowledge only about their neighbors, right? So this is a very, it's a nice algorithm. It has scalability, right? It can scale to large networks, which is why the internet, which is a two-tier network, autonomous system, right? The internet is divided into autonomous systems, and then within an autonomous system, you have these routers owned by maybe a specific ISP. So we saw that between autonomous systems, the distance vector algorithm is used, right? BGP is a distance vector type of algorithm. BGP was Border Gateway Protocol, all right? And so, distance vector has a lot of positive things going for it, but it had a pretty big vulnerability, right? A negative, a disadvantage. And the disadvantage was that after stabilization, so after stabilization, if the link cost changed, there could be some long time convergence issues. Okay, and we call it the count to infinity problem. All right, and it's basically due to something called routing loops. Right, so here's an example. In class, we saw that bad news travels slowly. Right, we saw that when the link costs change. So the simple network I gave you was a triangle network, 3 nodes connected in a triangular fashion. We saw that when one of the links, when the cost increased, it took a long time to converge. So I want to give you an example now where when one of the links breaks, right, not just the cost goes up, the cost goes to infinity. When that happens, that this bad news travels slowly actually is at an extreme. Right, you get count to infinity. These nodes will ping pong back and forth all the way to infinity. So here's an example. I just augmented the triangle network with a additional 4th node D connected to one of the nodes. Right, now let's assume that the network has stabilized. So distance vector in this case will stabilize quite rapidly. Right, now let's say that after some time, link CD breaks. Okay, meaning the cost goes to infinity. Of course, both C and D will recognize this fact because it's neighboring to them. It's adjacent to the nodes. So specifically, C will recognize this fact. And what will C do? So when a change happens, when a node learns of a change, what does a node do? In distance vector. Okay, so I think back to distance vector algorithm. Remember, for distance vector and for link state, for each of those, I told you there was one principle you needed to understand. So for distance vector, what was that one principle? Iteration is part of it. There was one principle. Yeah? It's okay, you're stretching, but do you know the one principle for distance vector algorithm? So updates is neighbor is part of it, but what's the one principle? What's the single most important principle of Bellman-Ford of of distance vector algorithm? There, I told you now. So I just said the answer. I guess you didn't recognize it. It's okay. So what's the single most important principle? Or what's the single principle behind distance vector? Yeah. That's link state. Okay, so right, link state algorithm was be greedy at every point. For distance vector, what was the single principle? Bellman-Ford, which is correct. Choose the best neighbor. And that's the update. Okay? And then you iterate on that. But it's all based on Bellman-Ford. So when node C learns of the change, what does node C do? What does it do? It runs Bellman-Ford, right? Because it saw a change, right? So it's going to run Bellman-Ford, and what is it going to do? It's going to look for a route to D. Now, its own route to D has broken, but what does it know about A and B? Do A and B, before the link broke, did A and B have routes to D? Yes or no? Yes, they did. So C is going to mistakenly use them. It's going to ask A. It's going to know from A had a route to D. Route to D, yeah. And it's going to use it. It's going to update its distance vector through A or B. And then it's going to tell A or B. And what are A or B going to do? Well, they were using C to get to D. So they're going to update their distance vectors. And if you can see, this is going to go on forever. Because there's no alternate route to D. Because there's no alternate route to D, this is going to go on forever. And this is essentially what's called a routing loop. Because C is using A and A is using C. Okay, so let's say it's A. Right? C is going to try to use A to get to D, A is going to try to use C to get to D. And since there really is no eventual route to D, they're going to ping pong back and forth forever. So this is an example of the count to infinity problem. All right, where they will really count off to infinity unless you put in a policy to stop that from happening. Okay? So any questions about this? I mean, what do you really want to happen? Well, yeah, I mean, you want... So if you go onto your terminal or your command window and you ping a host that doesn't exist, what does ping give you? Either gives you a timeout or host not reachable, right? It depends on how ping is written. That's what you really want. There's no more route to D. In this network, there's no route to D. In the example that I gave in class, there was an alternate route, which is why you ping pong back and forth until the alternate route became preferable. Here, there's no other preferable route. Okay, so this is the simplest example I can think of. Well, maybe it's not even a simple. Can anybody think of a simpler example where count to infinity happens? I'll give you a hint. I don't need one of the nodes in this example. No, in the triangle network, there's always a route. It's a fully connected network, and there's two routes. So if one route fails, that's what happened in class. One of the nodes here is unnecessary. Huh? Yeah, either B or A. Meaning a linear network with three nodes. Right? ACD or BCD. Just those three nodes with two edges will suffer the count to infinity problem. Okay? So there. So I hope you have a slightly better understanding of count to infinity. I've uploaded these slides to Luminous files. Okay? Yeah.
Question about how we would update both A and C after while trying to get to B to get to D.
Yeah, I mean, some of this depends on policy.
Yeah.
right? How you break ties and so on. Yeah. Yeah. I mean, like A could try to use B or C could try to use A or B could try to use A or C. But in any case, they all fail. You will get to count to infinity. But you're absolutely correct. It's not deterministic. It depends on policy. How? Because right. Remember when you have two paths that are the same, you flip a coin. Yeah. Okay. So any other points? Any other questions or doubts about distance vector and count to infinity? So a little bit of review, but a little bit of a new example about count to infinity. Still have a doubt? Chen-Hui, anything? No? Okay. Okay. This didn't seem to. Oh, hang on. It didn't update. It's very strange. It says on slide 2. Okay, there we go. Oh wait. So yeah. Yeah. Anyway, so this is the count to infinity, and then remember there was a couple of solutions. One was Poisson reverse, where a node lies to another node, right? So remember, the core of the problem here is that A is using C to get to D, and C wants to use A to get to D, right? And so you could have nodes lying and so on, but the only real way to so in class I told you about this. What's the only real way to fix routing loops? Yeah. So somebody said it here? Someone else? What's the only way to fix routing loops in distance vector? There's only one surefire solution. Do you know? Yeah, add path information. So not necessarily record the path, but share paths, right? If A is using C to get to D, along with the costs, remember nodes share their costs. They share their own distance vector with their neighbors. In addition to the distance vectors, you share the path that you took to get that distance vector. Okay, and I think I have an example of that here. This is, I took from RFC 4271, which is for BGP, that there's a clause in there which tells you exactly how distance vector routing is done. If you read it, so it's in the AS path. So AS is autonomous system. Remember I told you internet is two-tier. So there's a field called AS path, which is what is a sequence of autonomous. So at the AS routing level, what's a sequence of ASs that you take to get to from one AS to another? And so AS loop detection says you scan the full path in the AS path attribute, and you check if the autonomous system number of the local system is in that path. If it is, you don't prefer that path. Okay, so this is how you prevent routing loops. This is how BGP does it. Okay, but of course you could do the same thing within an autonomous system. Inside of AS, you have a path which is a sequence of nodes. Yeah.
Does the node have to know the complete path or just the next neighbor where it has?
No. So this is a good question. Do I need to know just neighbors? It turns out that this problem can happen on a much wider scale. And that's why Poisson reverse cannot fix it. If the problem only happened at the neighbor level, Poisson reverse could fix it, because I can lie to my neighbors. The problem is I can't lie to other nodes because I don't communicate with other nodes. So you could have a big routing loop, and Poisson reverse wouldn't fix it. So you need to send the entire path.
So but then we need the path to every destination in the node anyway.
No, so nodes share it. So my neighbors share. So remember, people are just sharing information with their neighbors, but they're sharing what path they are taking. And if the path that they are taking, if I am in that path, then I don't prefer that. Yeah. Okay? So I think so I hope we have a deeper understanding of the core problem and how to fix it. Okay? All right, so some of you are just coming in. We just reviewed count to infinity and how to fix it by, so we saw that the core problem with count to infinity was routing loops, and you fix it by sharing path information. And this protocol, in case you want, it's called the path vector protocol. So it's distance vector protocol augmented with paths. Okay, so we just talked about distance vector protocol. You can come talk to me later. Okay, and about routing loops. Okay, so it's a review of what we did before. I just went a little bit deeper. The second thing was in link state, Dijkstra, right? We saw that that this is a centralized algorithm as compared to decentralized for distance vector. Distance vector nodes need to know local information, neighbor. In Dijkstra and link state, you need to know global information, meaning every node, every edge, every label, every cost. All right? And we talked about in class, I didn't prove it to you, but it's almost believable that when the costs are non-negative, being greedy is optimal. Because when costs are non-negative, the accumulation can only grow bigger. Right? So I mean that's the kind of, let's say, qualitative proof. You can write this down. This proof is rigorous. It's just not mathematical. You could, so as if costs are non-negative, when they accumulate, they can only grow bigger. Right? They cannot grow smaller. Maybe that's more accurate. They cannot grow smaller. Right? So being greedy doesn't hurt you. Okay? Now, when the edge labels can be negative, right, then you no longer have this assurance that the accumulation of costs will not decrease. Right? In the future, you can get a large negative edge and it can decrease. So I've given you 4 networks here. Let's start with the one on the upper left. Okay? On the upper left, I have a 3-node network. And ABC, so the cost from A to B is -5, A to C is -2, B to C is 10. In this instance, what will Dijkstra give you? I'm going to, I think you guys are reading this. Okay, there you go. Don't read. Think. Okay? So let's take the one in the upper left hand. Okay? Nobody here has photographic memory, right? You have photographic memory? Huh? So upper left. So let's look at the one in the upper left. What will Dijkstra give me? So so A is the source. Okay? I want to build my shortest path spanning tree from the source, A. So what will Dijkstra give me? Tell me. Yes? Yeah, it will give me, so I think this gentleman here is computing. Tell me what you got. Yeah, you, hi. What did you get? No, so specify the edges in the spanning tree.
A to B to C. A, B, AC.
Yeah.
Then AB is smaller than AC, so it's AB. So -5 go in.
Yeah.
Then after that, the next one is C. So the distance is either -5 -10, which is 5, which is not. So you take -2. So AC is -2.
Yeah.
So -5 -2.
So those are costs. I said specify the edges in the spanning tree. The edges are defined by the nodes that are on the endpoints. So,
You take the -1 H and the -2. AB and AC.
yeah. Okay, let's do that because the cost could have been you don't specify edge by the cost. That's not unique. So I think you got the right idea. I'm just saying let's use if I don't tell you this is edge 1, 2, 3, the edge between A and B we call AB. Okay? So both of you are correct. Dijkstra gives me AB and AC as the shortest path spanning tree. Okay, now is this correct? I think you showed it was correct by running Dijkstra in your head, right? Yeah, you did. You ran Dijkstra. So is this so the rest of it, is this correct? Yeah, this is the correct shortest path spanning tree, even with negative edges. So Dijkstra can work with negative edges. Let's go to the network in the lower left. What will Dijkstra give you? So now we're in the lower left. What is the shortest path spanning tree that is returned by Dijkstra's algorithm? Just hang on a second. Let me. Sid. AB and what? AB and BC. No, just give me the two edges or three edges, whatever it is, that are in the spanning tree. A, B, B, C. Okay, so who agrees? Who thinks this is okay? Raise your hand. So Sid, this is your classmate, has put forth that A, B, and B, C are the two edges in the spanning tree. So if you agree, raise your hand. If you disagree, raise your hand. So Sid, what do you think? Huh? Okay, good. So who? Yeah. Just AC. What are the edges in the spanning tree? AC and BC. Okay, who agrees with that? Sid, do you agree with that? What does Dijkstra's algorithm return? From A. Not from A to C. We don't need to specify a destination because Dijkstra computes the shortest path spanning tree from a node, from a source node. AC and AB. So, do you agree with that? Yeah. AC and CB. So we have all three possibilities. We have AB, BC, AB, AC, and AC, CB. Huh. Okay. You? Tell me.
Oh, I agree with AC, CB.
AC, CB.
Or does the arrow matter?
Are they directional? Are the edges directional?
Yeah. This is a directed graph. Yeah. Okay, sorry about that. Yeah, all these graphs are directed. There's an arrow here. Yeah. So this goes this way, and that way. What? A, B, B, C. Okay. So what is it now?
A, B, B, C.
Okay. Yeah, so what about you? Sorry about I thought I mentioned it up there, but I realized I hadn't. It's the same set of arrows. This is a directed graph. So you have to follow the arrows. Okay, so in this case, you say it's what? A, B, B, C. Okay, and what do you say?
I agree that it's AC,
A, C, A, B. Okay. So let's run Dijkstra. You start at A, and what was the principle of Dijkstra? Be greedy. So what's the first edge you're going to add? Sid? Okay, and then what's the second edge you're going to add? You have to follow the arrows, right? So yeah, so the next edge is what? AB. So Dijkstra is going to return the same as the one above, right? AB and AC. That's going to be the shortest path spanning tree. Now the question is this correct? Yes or no? What's the correct shortest path spanning tree? A, B, B, C. Right? I think that's what you were saying before, right? That's the correct shortest path spanning tree. It's not the output of Dijkstra. So this is an instance with a negative edge. So I tried to come up with the simplest example. Right? Here, the negative edge is sort of just one level away. Right? It's not neighboring, so I cannot use it when making a greedy decision. So this is an instance where the negative edge screws around with Dijkstra. Okay, so Dijkstra's algorithm terminates, but does not return the correct shortest path spanning tree. So everybody okay with this? Sid? The rest of you? So, some of you raise your hand to one of the others. If you have a question now, now's the time. I think you're okay? I'm just pointing to people who answered me. I want to talk to the rest of you. Yeah?
So Dijkstra terminates when every node is in the...
Yeah. Yeah, when you get your spanning tree. Yeah. So we discussed this. Let's make sure that we understand. Will Dijkstra's algorithm always terminate? So I would say, so who says yes or no? Give me a show of hands. Will Dijkstra's algorithm always terminate? Yes or no? Who says yes? Who says no? Okay, tell me why. Yeah. Yeah, so if there's a negative cycle, I agree. But maybe it was a bit of a trick question. Because, yeah, so these are semantics. I'm never going to try to trick you. Right? But as long as we understand everything, if we actually say run Dijkstra, that means the problem makes sense. With a negative loop, the problem doesn't make sense. But yeah, you're right. You could say it doesn't terminate, or you could say I wouldn't even run Dijkstra, because there's no answer. With a negative cycle, there's no answer. The question of shortest path makes no sense. Okay? But good. Okay, as long as so let's go here. Upper right. So compute the shortest path spanning tree that's returned by Dijkstra, and what's the correct one? So is this correct? Will this give me the correct shortest path spanning tree or not? So again, if you're stuck, right? You say I'm computing from A, okay? From A, and it's a directed graph. If you're stuck, what you need to do is say start at A, and make the best decision. So what's the first edge in your shortest path spanning tree? AB, right? Because 1 is less than 100. What's the second one? BD, right? And then AC. So the shortest, so the spanning tree returned by Dijkstra has edges AB, BD, and AC. In fact, in that order. Okay, remember, if I want to know if you understand, Dijkstra, one way is I can tell you what order do the edges get added in. I don't need to check your work, right, to see that you can do the math properly. Actually, I don't care how you do the math. But if I ask you what order you add them in, that tells me that you understand. So in this case, in this case, is this correct? Is AB, BD, AC the correct shortest path spanning tree? No, right? So what would be the correct one? Yeah, it'd be AB, right? Then you actually, to get to D, there's a better path, right? Now, the only way to get to C is through A, so AC has to be there, but then you want to add CD. So the correct shortest path spanning tree is AB, AC, CD. And this is another example where Dijkstra that doesn't return it. Okay? Lower right. So what happens here? What does Dijkstra return, and is it the correct shortest path spanning tree? So again, I think the first edge you would add, we can all agree, I hope, is AB, right? Then what? Yeah, then you actually have a choice to make. Because if you add BD, that's cost 100 from A. If you add AC, that's cost 100. So you can actually flip a coin. Unless you have a tie-breaking rule. Right? It turns out you can actually have tie-breaking rules. You can formulate any tie-breaking rule you want. The one I gave you was flip a coin. Right? If you flip a coin, then half the time, if it's a fair coin, half the time you would choose BD. And then you get the wrong shortest path spanning tree. Half the time you'll choose AC, and you'll get the correct one. Okay, but you can have other tie-breaking rules. Okay, I mean, if you want to, if you think carefully and deeply, you can. So you might say that if I have a tie-breaking rule, I choose the edge that's closest to the source. Right? Let's say I give you that tie-breaking rule. Choose the edge that's closest to the source. Then which one would you choose here? You would choose AC, right? I'm just saying that's a tie-breaking rule. And some tie-breaking rules make some sense. Okay? But anyway, I'm not going to dwell too much on that. So do we understand some of the, let's say, subtleties of when Dijkstra works and doesn't work? Okay? Now remember, in all of these, you were able to compute the shortest path spanning tree by inspection, right? So remember, don't turn off your common sense. Right? In all of these, if I tell you what's the shortest path spanning tree, you have to understand what does the spanning tree mean, that's all. And you can pretty much eyeball it. Okay? And that's an important skill, right? Especially in small problems, in toy problems, that's an important skill to make sure you understand about what's going on. Dijkstra shouldn't just be a mechanical algorithm for you. It should be an idea. Okay? The shortest path spanning tree algorithm is an idea here. Okay? And you should be able to execute it, right? Like without writing a complex algorithm. Okay, any questions? Okay, so that was about Dijkstra. Let's try to wrap up. I think that's all I have here. So this was nothing but, let me see. Yeah, I was there. I don't know what happened. Hello? What just happened? Yeah. I don't know what happened. What did I do? Because I wanted to open this. Is there like a... Wait, somebody's messing with this. No, I'm not kidding. I didn't move that. Do you see the mouse move? That wasn't me. It's weird. Okay, that was weird. I wonder if the people videoing are helping me. No, really, I didn't do that. All right, I was having a problem. Like it's something to do with desktops, right? There's multiple desktop, and I didn't activate it. Okay, anyway, this is very odd. Is it here? No, I don't know what that is. Okay, So I also uploaded a set of slides called 3 questions, 3 why questions, and these were the 3 why questions that we've been asking throughout the semester or throughout the second half, right? But why MAC and IP, why retransmissions at both layers, and then there was one about why are there checksums at all these different layers. And basically the way to think about it is that a layer in the network protocol stack is nothing but a function call, right? And there's no reason why you can't have something go wrong in the computation, right? I mean, due to some error in the code or something in memory. So there can be errors when transferring data between layers. Sometimes, as you know, in a router, for example, data is only processed up to the network layer. So if you just leave the checksum at the transport layer, then the intermediate routers won't be able to access it. Some of the other ideas I had. So the checksum is different at different layers. So it's actually it's checking different parts of the payload. And the checksum is just an error detecting code, right? And you can actually have situations where you can have errors, but at the end of the day, it's still consistent. There are undetectable errors. Okay, it's not that every error is going to be detectable, right? For example, if an error, like I told you, it's an error detecting code. So if an error pushes you to a code word, it's not going to be detectable at a certain layer. But since the checksum is different at the different layers, the checksum at another layer might be able to catch the error. Okay, so there are a variety of reasons. So remember, I told you in IPv6, actually, they take a different approach. I think there's only a checksum at one layer, at network layer. Okay. Okay, so I wanted to close the loop on the 3 why questions. Okay, I know we spent quite a bit of time on at least 2 of the 3 questions, but remember, the point there is not the answer. The point there is the series of questions that you ask. And I hope you understand, right? We went through asking a series of questions. So, and I think you learn a lot by asking those questions and trying to sort of, disentangle what's going on there. Okay, so this is the second thing I wanted to sort of close the loop on. Right? The third thing, hang on. The third thing was, I promised you, here we go. Okay, I want to say something about an event that happened in the real world. I saw some interesting cartoons. So this is so we did the OSI stack, right? The Open Systems Interconnect stack. But then somebody said this is like the new stack, right? You have Google, Amazon, and then some stuff in between, and then Facebook. So anyway, I thought that was kind of funny. All right. For those of you who know me, this is my favorite cartoon of all time. Have you seen this? Yeah. Right. So there's this dog in front of a computer, kind of older dog, talking to a younger dog, and he says, "On the internet, nobody knows you're a dog." Right. And this actually is a good segue into what I want to talk about, which is how YouTube was hijacked. And this is the core of the problem. On the internet, nobody knows you're a dog. Right? That's kind of, so it's my favorite cartoon, but it's also related to what we're going to talk about. All right, so it starts off with this idea of origin authentication and the lack of it in internet routing. Right? Meaning, if I send you a packet, you know it's from me. But am I who I say I am? That's the core problem. Okay? You don't know that I am who I say I am. All right? And this allows something, or it enables something called route hijacking, which is an arbitrary node or router can originate as the sort of source of a range of IP addresses. Okay? And then if somehow this claim, this fraudulent claim that I am, for example, Google, or I am YouTube, if this claim can get spread, then the entire world will think I am YouTube, or Google, or whoever, or Facebook. Okay, and then traffic will be diverted. So let's try to understand what happened. This is something that actually happened. So this is probably, maybe, do I have a date? Let me see, hang on. In 2008, the same, interesting, February 24th. That's actually, February 24th, that's actually 4 days after my daughter was born. I never connected it. She was born in 2008. Okay, so around that time, YouTube address space was covered by this range of address. Right? So now we understand what this means, right? 208.65.152.0/22. what's the meaning of this? Is this one address? Or is it a range of addresses? It's a range of addresses, right? I'm telling you the subnet part, right? This is the CIDR representation of a range of addresses. So it's the aggregation of all of the address space that is covered by YouTube. Okay, and YouTube is, routers around the world are using this 22-bit prefix and saying if something is destined for this 22-bit prefix, send it to YouTube. Right? Send it to the autonomous system that YouTube lives in. Okay, and people were, I just took a random picture here. This is a random shot of the YouTube screen. I think this was done in like 2010. Okay, so this is YouTube space. Okay, from router to router, the destination MAC becomes the destination of the next hop router, and the source MAC becomes the MAC of that node that's doing the transmitting, that's doing the forwarding. Okay, so it does change it. Okay. Yeah, if you didn't know, there was a blackout. So we had about 15 or 20-minute lecture in darkness. Yeah, but it was cool. I felt like a celebrity or something, up here it's dark. I may have to run lectures in the dark from now on, like on purpose. Okay, let's go back here. So we just use the slides because it's possibly more useful. Hang on, it's in downloads. Okay, so this is just a bunch of Q&A. If you can come talk to me about what you missed, okay, or talk to your friends. If you have questions, just come see me. So for those of you who came late, if you have questions, you can come and see me. Okay, so we already did this one. So the answer to this is false. Okay, how about this one? When an IP router, okay, so this is the same question, but when a router forwards a packet, it does not modify the destination IP. So this was destination MAC. This is destination IP. This is true or false? So we're going to do this. I decided for this because there's so many questions. I didn't set up the poll everywhere. Okay, but let's do this old school. Okay, you have hands, right? So there's two answers, false or true. Try to participate because I tell you this, there's some value in committing to an answer, even if you're wrong. Because if you're wrong, your brain will make the connection what's right. So, work with me, okay? Make the connection, as in, take a position. So is it true or false? Who says false? It does not modify the destination IP. Okay, so you must raise your hand to either of these, okay? Who says true? Okay, so the destination IP address does not change. It remains fixed. Yeah? Oh. In a NAT table, the destination IP doesn't change one way, but it changes the other way, right? Yeah. You're talking about sort of from first principles, I would say you would ignore that, right? Because if we're just talking about fundamental networking, if we're just talking about understanding what's going on, you ignore it. But you're absolutely right. If you now bring in some complexities like NAT, then it's a bit trickier, right? Yeah. So we're not talking about on a test, okay? The fact that you asked me, I'm not worried about you. Because you understand, right? Now, if you're talking about a test, I guess if you make me understand that you're talking about with NAT or without NAT, then both answers are acceptable. Okay? But it's kind of, if it's just a true false, it's hard to, know that my aim is not to trick you. Okay? So I would intend this to be true. The destination IP does not get modified. Okay, are those of you who had said false, are you okay? There were a few people back there. If you have questions, just ask, okay? Right, remember, so we used the destination IP. We use IP address to go long distance and MAC address to route in a local area network, right? And remember, we had this long discussion about why MAC and IP, right? That's how it's done, okay? And in that discussion, we talked about how they are used. Okay, how about this one? An organization is granted a block of classless addresses with addresses starting from this 199.34320/27. How many addresses are granted? So what's the answer here? How many addresses are there in this range? So guys in the back row, Daniel? Yeah, how many addresses are there in this space? What? 16, okay. So anyone else? Yeah? Okay, so we have a 16 and a 32. So anyone else? Okay, so let's say that it's between, it's not 8. Okay, I'll give you that, it's not 8. Okay, so let's say it's one of these two choices, okay? So again, a binary choice. Okay, who says 16? Daniel? How about the lady who just walked in? Hi. Can you take it up here and give me your best guess? And who says 32? So are you 16 or 32? But you got to tell me why. And it cannot be that I saw more hands for 32. It's okay. Just think about it. I'll give you a moment. Can you pick A? I know. I knew that you or your friend was going to say that. You guys are a problem. Yeah. Yes, you can say A because why? You think it's like 30 or something like that? Yeah, something like 30 maybe. Yeah. But notice I said how many addresses are there. I didn't say how many hosts. That's the difference, right? Do I understand you? Do you ever watch that show? There's a show called Penn and Teller Fool Us, where there's these two magicians, like they're really famous magicians, and other magicians come and do tricks and try to fool them. And they're supposed to, Penn and Teller are supposed to, like, decide if they got the trick or not. But they don't want to give away the magician's trick. So they speak in code. So they say, if you know it, they would say some stuff. Do you know what I'm talking about? Like, this is like, I'm not going to say the answer, but do you know what I'm talking about? Do you think I know what you're talking about? I think so. Okay. So, hi. Why is it 32? Hey, guys, just quiet down for a sec. Yes, please. They're part of the subnet. 5 bits in the host part. Yeah. Daniel? Yeah, so it's 32 minus 27. So there's 5. So the way to understand this is there's 27 bits in the network part. So that 27-bit prefix specifies the subnet. The remaining 5 of the 32 bits specifies the host. So there's possibly 2 to the 5 addresses. Now, someone could say, hypothetically could say, hey, but you can't assign all zeros and all ones to a host. So that's true. So it would also be okay to say there are 2 to the 5 minus 2 possible hosts in the network. Okay, so both of these views are okay. I'm not a stickler for this is the right answer. Okay, it's about understanding, right? There are really 32 5-bit binary vectors. It's just that we say I don't want to assign specific ones because they're reserved. So it's good to understand both aspects of it, okay? But in this case, I would say they're addresses. There really are 32 addresses, 32 vectors, right? If I had said hosts, even with the host, I would accept 32, right? But if somebody said that there were 30, that's actually more accurate because we technically don't assign all zeros, meaning all zeros are all ones in the host part because all ones is the broadcast address and all zeros is the network address. Okay? Okay, are we good? Are good on this? So here I'm, thinking of 32 as the right answer. Okay, how about this one? Just a little bit of reading. Let's see. An IPv4 datagram is fragmented into 3 smaller datagrams. Which of the following is true? Okay, so this is the fragmentation and reassembly function that's implemented at network layer. So please read these 4 and see if you can. So the do not fragment bit is set to 1 for all 3 datagrams. So this means that you can never fragment this fragmented packet again. Is that true? What do you think? No, right? There's no reason why a follow-on network couldn't impose another constraint. So it's not A. How about B? The identification field is the same for all 3 datagrams. The more fragment bit is set to 0 for all 3 datagrams, and the offset field is the same for all 3 datagrams. Right? I think C and D you can see are not true because you need to differentiate between datagrams, right? The fragmented datagrams. So it's really B, which is that this identifies they're part of the same parent packet. So here the answer will be B. Okay, so this is just reading through and sort of doing some process of elimination. Okay? So are we good? All right. The value in the sequence number field of a TCP segment defines the number of the blank data byte contained in that segment. Is it the last segment, the last byte, the next byte, or the first byte? The sequence number field, okay, the value in the sequence number field. Remember in the TCP header there's a sequence number field and there's an acknowledgement field, right? So here I'm talking about the sequence number field. So what is that? The value tells you what? It's the number of the last, next, or first, or some other byte contained in the segment. Like, what's the most obvious thing? What's the most natural thing? Yeah? What? First, yes. And that's what it is. Right? If you're going to represent this whole sequence by one number, I'm going to represent it by the first number. Right? That tells me the starting point. Okay? The number of the first byte. So here, this is the first byte. The acknowledgement field defines the number of the blank byte a party expects to receive. This one would be what? This is the way we acknowledge. Remember the clever way of acknowledging in TCP? What do we do? The next byte, right? So this is the, in the acknowledgement field, you put the number of the byte you are expecting next. Okay? So remember, this is that cool idea that gives you cumulative acknowledgement, and it allows you to do what? What is that preemption of timeout called? It's called fast retransmit, right? And it's this way of acknowledging that allows us to do that. Okay, so this one is next. If the ACK value in the TCP header is 200, then which byte has been received successfully? 199, 201, or 200, or some other? Yeah. Yeah, 199, right? Because it's the next one I expect is 200. That means I got 199. Which of the following algorithms solves the single source shortest path routing problem? Yes, we should know this, right? We only studied one of these algorithms. Which one did we study? We studied Dijkstra, right? So yeah, Dijkstra is the algorithm to find the shortest path in a graph rooted at some node. I call it source. So single source, shortest path spanning tree or routing problem, okay? The other algorithms are related. Like I think Prim's algorithm is, so Bellman-Ford, actually it turns out Bellman-Ford can be modified to also do shortest path routing. But the way we did it was essentially to do distance vector, right? Floyd's algorithm is another algorithm to solve the shortest path routing. Prim's algorithm is a way to find the minimum cost spanning tree, okay? So here I want Dijkstra. Somebody asked me a question. I don't know if this person is here, about the homework, and where I asked you to compute shortest path route, minimum cost spanning tree. It wasn't you, right? No. Somebody asked and they said, oh, do you mean like Prim's algorithm or whatever? We didn't study that. So if you're here, I think I replied to you, but what I meant is you do it by inspection, right? You can compute the minimum cost spanning tree by inspection. If it's not too difficult, you can just compute all of the spanning trees and know what the minimum cost spanning tree is. Okay, so don't forget that. Remember in class I told you, you know how to do routing. For many of these problems, if you understand the question, you can use sort of just brute force computation to find the answer. Okay, so this is Dijkstra. Dijkstra's algorithm may not terminate if the graph contains negative weight edges. True or false? So is this true or false? Come, guys. Who says it's false? Who says it's true? Okay. So why? Why is this true? Huh? It says may not terminate if the graph contains negative weight edges. Okay, so yeah, so let's clear that up. If you had a negative loop, then you would never run Dijkstra, right? Because do you see why? I think you see why now, right? What? It's not that it wouldn't work. Yeah, Dijkstra is a tool to solve a problem. That problem has no solution. So it's not a problem with Dijkstra. It's a problem with the problem. But I think there's a little bit of confusion, and I kind of can accept other answers. But I'll just tell you my position. You can have your position as well. But my position is if you're going to apply Dijkstra, the problem has to make sense. So I would say here that when you can apply Dijkstra, it terminates. It's a deterministic algorithm. But I'm also okay with the position that if there's a negative loop, yeah, it won't terminate. But it's not that it won't terminate. That seems to imply it can find an answer. There's actually no answer, right? Yeah. Okay? But it's okay, as in most things. If you can point out these things, I'm not worried about you. That means you understand the basic idea, and you understand the slightly more subtle points as well. Okay? Are you guys okay with this? Yes or no? Yeah?
It is, but the question, in my opinion, is like you run Dijkstra on a negative weighted instance, and then that, but it doesn't say anything about
The loop.
yeah, if there is a loop or not.
Yeah, often what you do is you need a pre-processing step to check for loops, negative loops, yes.
But are you saying that this question implies that you have done that?
It doesn't imply that, but it implies that you can find an answer, right? Yeah. But as I said, it's a matter of semantics, and I wouldn't hold anybody, right, to this position or that position. It's more important that you understand both positions, right? Getting an answer to this gets you nowhere. It doesn't matter whether it's false or true. If you tell me if there's a negative edge, if there's a negative loop, the algorithm won't stop. Okay, I'm okay with that because you understand there's a point about negative loops. Yeah. So okay, but everybody clear, right? Right, that you can have arbitrary graphs if you have a negative loop. Clearly, any algorithm will go on forever, not just Dijkstra. It's not a function of fault of Dijkstra. It's a fault of the problem. There's no shortest path. You can go around the loop forever, and if it's a negative cost loop, you can keep decreasing your cost. But forever. Yeah. Yeah, actually, you got a good point. Yes, you have a good point. Yes, so I think if you look at the way the vanilla Dijkstra that we talked about, without backtracking, right? I think some of you in an algorithms class, you've studied Dijkstra, but the way you define Dijkstra, it had backtracking. But vanilla Dijkstra has no backtracking. Dijkstra with backtracking is Dijkstra with backtracking. It's not Dijkstra. Okay? But again, maybe semantics. But I think that Chenwei makes a good point, and I lost my train of thought too. You're right. The way I've defined Dijkstra, it will always terminate. Right? But I think more importantly, with the negative loop, the question doesn't make sense. So you can't say if Dijkstra is right or wrong, because there's no answer. Does that make sense? Okay. So thank you for that. Okay, anything else about this? Are you okay? Because we had the discussion before. Yeah.
So the answer is false, right?
I think it will terminate. Yeah, correct. It's false. And I think it has nothing to do with loop, right? The vanilla Dijkstra. Yeah, vanilla Dijkstra will terminate in n steps if you have n nodes. Yes, and I knew that. So I just lost my train of thought with the loop. Okay, okay, for what values of x will Dijkstra's algorithm work and not work? So I think we can figure this out. So again, the assumption here is that this is the source. So this is a directed graph. This is the source. 1 is the source, and I want to compute the shortest path spanning tree. So for what values of x will Dijkstra work and not work? So you can set this up as an algebraic equation, right? So you would do what? 4 plus x, right, is less than what? 2. Right? When 4 plus x is less than 2, Dijkstra will not work. Right? And you can solve for x. So let me see. I think I did it. So it would be what? X less than minus x less than minus 2. Actually, for x equals minus 2, it doesn't matter, right? Dijkstra does, it's because the path from 1 to 3, 1, 2, 3, and 1, 4, 3 have the same cost. Okay, so I would take that for x. In my solution, I wrote x less than minus 2. I think I'd be happy to make it less, to say that it's correct for less than or equal to minus 2. Okay? So for x greater than minus 2, Dijkstra will find the shortest path. For x less than minus 2, it won't. For x equal, I say it works. Okay, are we good for this? Okay, so we can sort of generalize our idea of how to make Dijkstra work and not work by having some unknowns and setting up algebraic equations to find constraints under which it will work and will not work. Okay, please ask questions if you have it, okay? If you have any doubts, this is the time. You don't have to just hold it in. It's best to get your doubts cleared up. Okay, without knowing the values of so CWND is the value of the congestion window, right, from TCP congestion control. So without knowing CWND or the window advertisement, so window advertisement is the thing that does flow control, right? It's the receiver telling the sender, oh, don't exceed this window, so it's flow control. And CWND is what does congestion control. By observing only the sequence numbers of successive segments transmitted, is it possible to determine whether flow control or congestion control is operating at any given time in a connection? So the question is, without knowing these values and just by observing the sequence numbers, can you tell if you're in flow control or congestion control? No. So flow control, if you remember, is an advertisement from the receiver to the sender. Okay, and congestion control is the sender determining congestion. So I'm just saying here, you don't know the congestion window or the flow window. By just observing the sequence numbers of successive segments, can you tell like which one is the constraint? Yes, I mean TCP is running, but which one is the constraint? So this, I put this question here because I really just wanted you to rethink what's going on in TCP. So this is probably a slightly longer exercise for you. So I hope you, at least for this question on question 12, you go back and review the mechanics of TCP. Okay, but I think you can probably guess what the answer here is. Do you have enough information? That's what it's asking. With just knowing the sequence numbers, do you have enough information? What do you think? Like, what's your guess? Yeah. I don't think you have enough information. So the answer here is no. Right? You actually need to know either the congestion window or the flow window, right? And you need to know the sequence numbers. Then you can figure out where you're operating. Okay, again, the point of this is to go back and review the mechanics of TCP. Make sure you understand what's going on. All right. Okay, so I mean, some of these few questions are just about understanding TCP. I think this just explains TCP slow start. What is its goal and how does it work? Maybe in the interest of time, remember TCP slow start. So maybe in the interest of time, I'll say something, but I would really like you to go back and articulate in your own words. So TCP slow start is a mechanism to learn the boundary of congestion very quickly by exponentially increasing the window size. Right? And I think in class I asked you, why is it called slow start? Does anyone remember the answer? I said it's very fast, but it's slow start. Why? It's still called slow start. Do you remember? It's not very slow. So why is it called slow start? Yeah, because correct. We don't directly jump to, for example, some large value. We don't say we go from 1. So let's say my SS threshold was, 128. I don't go from 1 to 128. I slow start to 128. Okay, so it's slower than directly going to 128, but it's faster than AIMD, than the AIMD, the AI part of AIMD. Okay, so this is slow start. Okay, let me see. All right, so assuming that the link capacity and receiver window are infinite, so I have a infinite link, infinite capacity link. The receiver has no buffer constraint, so flow control is not going to kick in. How many round trips times does it take in TCP to send the first 10 packets? And then I say, in general, how many round trip times does it take to send the first K packets? Excuse me? Maybe this is my initial slow start. Yeah, you're right. Otherwise, you're going to be clipped, right? Yeah. So, like, what happens after two round trip times? Like, how many packets have I sent? So, assuming I start at 1. Okay, I will start at 1, right? So, I transmit 1. Then what happens after one round trip time? Like, what's my window size after 1 round trip time? 2. And then after 1 round trip time, what's my window now? 2. So that's 2 round trip times. How many packets did I send? 1 plus 2 plus 4. So how many? 7. So can you generalize that? That's all this is asking. Yeah, and this is the initial slow start. Okay, so it's just generalizing that. You can, so then after that, then I wrote, and anyway, so I think it just generalize that. It turns out that it's something like, oh, I think I just bounded it. Yeah. Yeah, but it's just 1 plus 2 to the 1 plus 2 squared plus 2 to the m. Okay? Okay, so a router with the given forwarding table receives this destination, packet with this destination. What is the interface that this packet will get forwarded to? So we're going to do longest prefix match, right? So how are we going to do it? So 128.195. So at least the first 16 bits match these three. So we know it's not ETH3, right? Dot 3. So this is /8. So that's just these first 8 bits. So it's definitely not this because it matches 16, right? So it's either this or this. Do you see why it's not ETH2? Because ETH2 has an 8-bit network address. And here we see that this is matching at least 16 bits of these three. Right? This has a 16-bit address and this has a 24-bit address. So for this 24-bit address, it has to match the first 24 bits. Does it match the first 24 bits? No, right? So we know it's not ETH1. We know it's not ETH2 because this is longer. So it must be ETH0. Okay, so the answer to this is ETH0. So everyone understand longest prefix matching? Okay? Okay, so for this one, TCP uses a three-way handshake. A two-way handshake could be potentially even more practical. Think about routing on the internet and suggest why a three-way handshake is used rather than a two-way or four-way handshake. So again, this is more of an open-ended question. So why don't we just use a two-way handshake? So why not use a two-way handshake? I guess that's the important question here. Why is a three-way handshake better than a two-way handshake? Any thoughts? If I'm going to start a connection, why should I have a three-way handshake? Yeah? Okay. But if I send 2 packets, there's been an exchange in both directions. Yeah. Yeah. No, so in that third packet, I acknowledge what? Yeah, I think you're on the right track, but it's not really about acknowledging, it's about something else. That third handshake is used to mitigate something that could happen on the second handshake. The return link may not be that good. Right? So if you just do a two-way handshake, now this two-way handshake sets up a two-way data connection, right? I might start to, the receiver could potentially start to send data without knowing that that link has been established. That's a primary reason for having a three-way handshake. So it's in the direction of what you said, Sid. You want to acknowledge, but you want to acknowledge so that now the receiver knows that connection has been established. Yeah. Okay? So again, this is to just get you thinking and questioning how and why things are done in current protocols. Everybody good with this? Okay, 17 just talks about the differences between link state, distance vector. I wrote vector, but distance vector and path vector. Right? Remember, so we had link state and distance vector, and then I introduced the path vector protocol, right? In which you just include the paths in addition to the distances. And so I want you to think about this. Which generates more traffic, which uses least memory, which can handle link additions and failures. So this again just involves some thinking. So maybe some of the ways to like work on some of these problems is to maybe get into a group and discuss. Remember, there's no right answer really. It's not about memorizing that this is the answer for this. It's about being able to think through, right? So for example, which generates more traffic, you have to ask yourself what has to be done to implement the network. So let's take a look at one of them. Which generates more network traffic in a large network? So what are the requirements of these three? Like what are the requirements of link state? It's centralized, but what are the, so when we say centralized, what we mean is that every node is computing the shortest path algorithm. Every node is doing it. So what does every node need to have? It needs to have the data of every other node. So what's a precondition to running Dijkstra at every node? You have to do something. There's a pre-processing step. It's a data dissemination step. And in a large network, there's a lot of data to disseminate, okay, which distance vector doesn't suffer. Okay, so which generates more network traffic? Again, it's not about knowing the right answer, but it's knowing that link state, there's a pre-processing step where a lot of data has to be. It's essentially, it's a broadcast problem, right? It's a many source, so all source, all destination problem. And that has to be done. Okay, so there's initially a lot of data that's generated. Okay, and again, you can go and work through by thinking about how you might implement. So for example, the least router memory, well, we know that, for example, the distance vector protocol only keeps information about neighbors, whereas link state keeps information about the whole network. So that already suggests which one is better. So distance vector in terms of memory and so on. Okay, so I'm happy to share my thoughts on this. If you have any questions, like you can think about it over the next couple of weeks. If you have questions, you can ask me. But this question is to just, again, get you thinking, talk in a group. Okay, the fundamental reason for which loops form in distance vector is that node A decides to use node B as the next hop for a destination that was at some point propagated by A itself. Give an example of this, draw a simple topology, break a link, and show a sequence of updates triggered by the distance vector protocol. So this is something I've already done for you. I want you to do it. Okay? There's something to be said for starting with a clean sheet of paper and drawing it yourself. Okay, again, I try not to harp too much on my theory of learning, but this is a good example. For me to give you an example and for you to sit and understand is one level of learning. To start with a blank sheet and come up with your own example is another level of learning. Okay, I want you to get here. Okay, you all are very smart, you can understand me. Now learn to create. Okay, so this is, come up with your own example. I've done several examples already, but come up with your own example and explain it in your own words. That's the point of this. Okay, we've done this already. We did it today, earlier today. We did this. I did it in class as well. Okay. Let's see. If TCP provides reliable in-order delivery of bytes end-to-end, why would you want to use UDP? Give an application that may be better off using UDP and explain why. So again, this is something we've already talked about. Just to give you a hint, it's less overhead, less resources, right? It's faster. You get better control of timing. Okay, but you should be able to articulate that in your own words with your own understanding of the two protocols. Only two more. This is what we discussed today about the Pakistani ISP and the YouTube hijack. And I said that we did it by hijacking part of YouTube's prefix. What does this mean? So again, the point here is I want you to be able to articulate that story in your own words. I've given you, we discussed in class, and because we did it without slides, I hope that you could almost, I tried to tell a story, right? So hopefully it sticks with you better. But the notes are there. The notes are complete. They also try to tell the story. But again, articulate in your own words, okay, about the example that I gave you. And my last question is this. Aggregate, and I put this in here because I wanted to make sure that that everybody understood this idea. People came in because people were asking me questions. Okay, so I want you to aggregate these 4 addresses to the highest degree possible. This is the inverse of what we did in class. In class, we said an ISP is given a block of addresses. It breaks it up into many, right? This is the reverse of that. If I have a bunch of ranges, right, I want you to aggregate them so that instead of advertising, for example, 4 prefixes, I can advertise 1 prefix. Okay, so do this now. I want to make sure everybody can do this once. Okay, and I'll give you a tip, at least for here, you can if you type IP, no, you don't need IP. You need just binary decimal converter. And there's lots of them, but there's one that I like because it works pretty well. Now I can't find it. I guess any of these will work here. Why can't I find it? Binary decimal online. I mean, any of these will work. Here, this one here. So this might be useful to you to convert between binary and decimal. Okay? So let's do it now. This is it. I don't have anything else here. Sorry. Okay. The other trick is that you see that these all have the same first 16 bits. So you don't have to worry about it. You just need to really worry about this byte. Right? So when so this is converting binary to decimal, this is decimal to binary. So how would you do it? You would take the IP address, you would convert them all to binary. In this case, it's just the 3rd byte that matters, right? So you would convert that to binary and you would look for a pattern. So it's 132, 33, 34, 35, right? So decimal to binary, 132, 134, right? 33, 134, 135. So let's convert that to binary. So what do you see? You first see that 1, 2, 3, 4, 5, 6. The first 6 bits are the same. Right? So what is that in binary? What is this in? This is 132. So we see that it's going to be 21256 okay? And then what? And then we see 01, 0001, 1011, right? These are the 2 bits that are for identifying the subnet. So can you tell me, based on this information, how you would aggregate these 4? Do you know? Okay. Even though it's fine, I want to ask you. I want to make sure everybody can do this because people were asking me questions, right? And if you don't know, please just ask. We'll settle it. We could even, we can stop it and do it after class because the answer is here actually, right? It's 212 56132.0 slash what? Slash what? 20 what? 22. Right. Right, because we see 16 plus the first 6 bits are the same for all 4 subnets. So the subnet part is 22 bits. Okay? Right, so it's so the answer is 212.56.132.0 slash 22. That's the aggregation of these 4 addresses. It's the subnet that contains all this. And here it's actually it's very nice. Right? Everything fits in nicely, yeah. These are good questions. In this case, I want to cover these 4 subnets. Yeah, but one could ask the question, how are you going to design a system? Then it's the question that you asked. Yeah, they're very similar, but in this instance, I want to cover it. Now, in this instance, it's kind of very nice, right? But it turns out that you can do things. I mean, with 4 subnets, it's actually there's not much that can go wrong. If maybe what I'll do in the next couple of weeks, I'll give you an example where it can be a little bit tricky, right? If you're talking about, for example, if instead of /20, like if I started to do it so that in this case the first 3 bits were identifying the subnet, but I only gave you 4, then it might not work out so cleanly. Yeah.
If we have like, if we remove 135 and 136,
Yeah.
then we can't.
Yeah. You can aggregate, but not in this clean way. Right? Then you have to ask the question, maybe you have to aggregate so that you cover this, but maybe a lot more. Yeah, that's not good, right? Yeah, then what you have to do is you have to have 2 aggregate IP addresses. Yeah. Yeah, like for example, if I made this 135.136, then I think it would get to the example that you gave where if I did my aggregation to be /21 to have to cover that, I would cover a lot more than just these 4. If I want to cover just what's here, then I need to have multiple aggregations. Yeah, so it's not so clean that everything is just one prefix. You'd have multiple prefixes. Yeah. Okay, but this is, let's understand the baby step here. This one is just, it's very clean. It just aggregates because you see here, right? This is 0, 0, 0. The last 2 bits are 0, 0, 0, 1, 1, 0, 1, 1. So those completely identify the subnet. And the first 6 bits are part of the network part. So 16 plus 6 is 22. So that becomes the network part of the aggregate. Okay? Okay, good. So let's end this. You have a quiz on Wednesday. I've uploaded a sample quiz to the Luminous file, so please look at it. Read the instructions because the instructions will be the same. Okay? And if you have any questions, I'm up here. Please ask me. And I'll see you on Wednesday at 11 a.m. sharp. Okay, because I'm going to give you 1 hour to do the quiz. So please come at 11. Thanks. Bye. No, it's sorry. Just guys, just stay 1 second. The quiz is not MCQ. It's MCE. You're allowed. It's multiple choice with explanation. You're allowed 1 A4 size help sheet, handwritten, please. Okay, and it will cover only the part that we covered in class. Okay, thanks.